Okay, good morning, everyone. Let's start our class today.
Good morning,
Morning.
Professor.
Good morning. And we did with the serial correlation, which is chapter 9, last week. And we did get to the section 9.4, which is the detection of serial correlation. And I hope everybody already reviewed what we have learned last week. So I will just start it from the first methods of detection of serial correlation, which is the Durbin-Watson test. Okay, and let me share the PowerPoint with all of you. Let me, okay. All right, this is what we call the Durbin-Watson test. Okay, you need to calculate, understand the Durbin-Watson statistic, which is the equation from our textbook 9.10. Okay, and the formulas is like this. Okay, and I like to explain a little bit about the range of the D. I mean this Durbin-Watson statistic D. Okay, there's three situations. The first one is for extreme positive serial correlation. Extreme positive serial correlation. When we say extreme positive serial correlation, means that the current error terms will be fully reflect what we have for the previous periods. Okay, in other words, the ET and ET minus 1 will be very close. Okay, so the difference of ET and ET minus 1 will be very small. Then you square it and add all of the observations started from the second. Why do we start from the second? Because we need to have T minus 1 for the first observations. Okay, in other words, with the numerator of these terms will be very small. So for extreme case, the D will very, very close to 0. Okay, for the second situation of extreme negative serial correlation. So on the opposite, negative serial correlation means these two terms, ET and ET minus 1, just the opposite sign, but very close to the magnitude. Okay, so in other words, the difference of these two terms will be like the 2 ET. Okay, then you square it, it turned out to be the 4 ET squared. And you sum of them, you can factor the 4 out. Therefore, the D values is close to 4. Okay, all right. And for no serial correlations, means the ET and ET minus 1 will be really random. Okay, there's no any patterns. Therefore, for no serial correlations, the D numbers will be in the middle of 0 and 4, which is D close to 2. With this information or concept in our mind, it helps us to understand the D values. I mean, the Durbin-Watson statistic. If we do the regressions and end up with the Durbin-Watson statistic D, which is close to the 0 parts or close to the 4 parts, or even in the middle of the D, D equal to 2. So in all this case, it will give us some ideas about the positive zero correlations or negative zero correlations, or even no zero correlation. Although we still have some formal hypothesis testing, and we do have some critical values or p-values to explain or conclude whether there's a zero correlation existed or not. All right, so you do, after you have these Durbin-Watson statistics, okay, then to test for I'm sorry, I think let me explain a little bit about the Durbin-Watson test, okay? And most of the econometrics, or maybe we put it this way, in most of the situations in econometric regression, we believe that almost never, this Durbin-Watson test never test the one-sided null hypothesis that is negative zero correlation. I think we explained it that in economic applications, most of the situation for zero correlations is related to positive zero correlations. So for negative zero correlation is rare cases, okay? So even this Durbin-Watson test, we never test the one-sided null hypothesis that is negative zero correlation, okay? And there's one thing for Durbin-Watson test compared with other tests is that before we do have rejection region and non-rejection region, but in Durbin-Watson test, we do have some inconclusive region, okay? We'll get to that. We'll get to the example, then I will explain where do we conclude with the inconclusive regions, okay? So, so after we understand the Durbin-Watson D statistic, then the formally test for positive zero correlations will involve these 3 steps. Okay, the first of all is obtain the OLS residuals from the equation to be tested and calculate the D statistic. I think we explained this one. The D is just like this. Okay, the second one is determine the sample size and number of explanatory variables. Okay, from this step, it is to check with the Durbin-Watson critical values to get the upper critical value or lower critical values. Okay, the third one is the null hypothesis of positive zero correlations is one-sided. Okay, so it turned out to be the alternative hypothesis is rho greater than 0, which is positive zero correlation. And null hypothesis less than and equal to 0 means no positive zero correlations. So remember, the Durbin-Watson test is related to the one-sided zero correlation test. Okay, and the appropriate decision rule, if we have the D lower critical value, DL, then reject the null hypothesis. Means the number is positive zero correlation. Okay, and if D is greater than D upper critical value, means do not reject. But sometimes we do have the D between the lower critical value and upper critical values, and it ends up with inconclusive region. Okay, and I think up to this point, in our textbook, it's also mentioned those rare case, if we do this two-way Durbin-Watson test. Okay, I think this is just for all of your reference. Most of the situation, we don't do this way, okay? All right, so we just listed it. I think the author always also listed it there for your reference in case that you need to do the Durbin-Watson two-sided test. Okay, so up to this point, let's get to the example, which is from our textbook. Okay, so would you please turn to the page of 306 of our textbook, which involve a regression. Okay, and this regression is about it's about the demand of the chicken consumption. Okay, so would you please turn to the page of 306, and there's a formula, it's an equation, regression equations for the model we want to estimate it, okay? And this is really from the data from our data set. And the name of the data set is CHICK9, CHICK9, okay? If it is also convenient for all of you, maybe you can also work on the e-views. And by the way, you can see how I did it, okay? All right, and let me explain this equation, the definition of y variables and x variable first. Okay, the y variable, y is per capita chicken consumption in pounds in year T. Okay, and there's a three x variables. PC is price of chicken in cents per pound in year T. And PB is the price of the beef, means the substitute. Okay, and the price of beef in cents per pound in year T. And YD is the US per capita disposable income in hundreds of dollars in year T. So we do have price effect, we have substitution effect, and also income effect for the demand of chicken in this equation. All right, so using this data, CHICK9, then I can estimate the equation PC, PB, and P and YD, okay? And open Person equation. Okay, then after I did it, I hit OK, and which is the equation of 914. Okay, I have already done it. So let me show this equation, 9.14. Okay, and I'm sorry that this screen is very small. I don't know how to make it bigger. Maybe I cannot do it. I don't know. But the formulas, the output is very smaller. And you also can refer to our textbook, equation 9.14. Okay, this is the regular OLS estimation of the regression. Okay, and from this output, would you please see the lower right-hand side, the lower right-hand side? We do have the Durbin-Watson statistic, which is the D. Okay, so the output, the computer is already calculated for us. Then it ends up with the number of 0.99299. Okay, so refer to our first step. Okay, refer to our first step. We have done this formulas, okay? And the first step is calculate the D, I'll say, okay? Then from the output, we have the D numbers. The second step is determine the sample size and the number of explanatory variables, okay? And according to our equations, and since we're the number of explanatory variables, it ends up with 3. We have 3 variables. And the sample size in these examples, how many sample size do we have? Let me see, how many sample size do we have? It's 29, okay? And 3 X variables. So would you please all turn to the end of our textbook, table B4, okay, which is on the page of 543. This is the table of critical value of Durbin-Watson test statistic, DL and DU. And this is for 5% one-sided level of significance or 10% two-sided level of significance. Okay, you all see that table?
Yes,
okay,
we have seen it.
Okay, the first column is N, is number of observations. We do have 29. So please, down to the 9 equal to 29. Okay, then from the second column up to the last, did you see the K equal to 1 up to K equal to 7? And locate K equal to 3, okay? And match with the number N29. Then you do see the lower critical value is 1.20 and the upper critical value is 1.65. Understand what I'm saying here?
Yes.
All right. Then remember the Durbin-Watson test statistic we have is 0.99299. Okay, then let's see. Let's see for these examples. Sorry. Okay. Durbin-Watson is 0.99. I think this is Durbin-Watson. This is D instead of. Okay. A Durbin-Watson is 0.99. Okay, here. And lower critical value is 1.2. Upper is 1.65. And what is the decision rule? If D less than 1.2 is reject null hypothesis. If it is up greater than 1.65, do not reject. And in between is called inconclusive. Okay, so what do we have for our D? 0.99, which is smaller than 1.20. So we reject the null hypothesis. Remember, what's the null hypothesis do we have for Durbin-Watson statistic? Is this. Okay? So our conclusion for this example end up with reject the null hypothesis. So from the Durbin-Watson statistic test, we do conclude that in this equation, in this example, we do have positive serial correlation exist. Okay, all right, this is the way we are using eViews. Okay, today I'm going to show many computers procedures and also the output. Okay, and this is using by eViews. What about Gradle? Okay, Gradle, we need to run the model. Use the ordinary least square and put the y as dependent variable and this 3 as an independent variable. Oh, sorry. Okay. What happened?
Because the price you're doing the dependent variable, the BC1.
Oh, that's all right. Then, okay, I put it here. All right. This is the regulars, OLS, okay? And I hit OK. So this is the output exactly as what we did in eViews. Okay, you can check with this is equation 9.14. All right, and we also have provided Durbin-Watson statistic here in Grados is 0.99299. It's the same as the eViews. Then how do I do the Durbin-Watson test from Grado? Okay, see it carefully, okay? I'll hit the test. Then did you see the Durbin-Watson p-values? So click the function of Durbin-Watson p-value. Okay, from Grados, it doesn't provide us critical values. It provides us the p-values. Okay, so for positive autocorrelations, serial correlations also called autocorrelations. The p-value is that small. Okay, in other words, this is the same result as we did it from the critical value approach. All right? Okay, understand it?
Okay, understand.
Okay, do it again, test, and check with the Durbin-Watson p-values. All right, so I have shown both eViews and the Grados about how to do the Durbin-Watson test. You all clear?
Yes, very clear. Thank you.
Okay, and after we done this Durbin-Watson statistic, and we need to understand, not all the methods are perfect, okay? And for Durbin-Watson test, there's a number of limitations. Okay, first of all, did you all remember that if you want to use Durbin-Watson test, there's 3 assumptions required. You'll remember that 3 assumptions? We may go back and review these 3 assumptions. Okay? What are the 3 assumptions required for Durbin-Watson test? First, the regression model includes an intercept terms. I don't think we have any problem with that. We all have intercept terms. Okay? The second one, serial correlation is first order in nature. Means that Durbin-Watson test always test first order serial correlation problems. And you all know that not only first order serial correlation, we do have other forms of serial correlations. But if you are in other forms of serial correlations, Durbin-Watson test cannot make it. Okay, the third assumption is the regression model does not include a lagged dependent variable as an independent variable. Okay, so far we haven't have any independent variable which is the lagged dependent variable yet. But when we get to the chapter 12, we are talking about the model with lag dependent variables, which is popular in time series models. Okay, so if you have the regression model which include a lag dependent variables as the independent variables, and Durbin-Watson test cannot do it either. Okay, So remember, the Durbin-Watson use, if you want to use Durbin-Watson test, the 3 requirements have to be met. All right, and the second problems for the Durbin-Watson test, the limitation, not really the problem, but the limitations, is the size of inconclusive region increases as the number of independent variable increases. So what do we mean by that? Would you please all get back to the table B4? Don't remember that inconclusive region is between, if we have the D values, which is between in the lower and critical value, the range of, between lower and critical values. If you check with the B.4, these tables, okay, just in terms of 29, we just have it. Since we have K equal to 3, so the lower and upper critical value is between, it is 1.2 and 1.65. Okay, so the length of this upper and critical value is 0.45. If we have the same observations, but K equal to 7, okay, if K equal to 7 means the number of independent variables increase, then the lower critical value is 0.9 and the upper critical value is 2.05. So the length of upper and critical value increases to 1.15 from 0.45 to 1.15. So this is what I'm saying, that the size of inconclusive region increases as the number of independent variable increases. Okay, this is one of the limitations. When we have this inconclusive region increases, means the probability to false on the inconclusive region is higher. So we may not end up with the conclusion that whether we test it is a positive serial correlation or not. Okay, all right. Therefore, since the Durbin-Watson test has these 2 limitations, one is 3 assumptions have to be met. The second one is the size of inconclusive region increases as the number of independent variable increases. Therefore, there's a second alternative, popular alternative to Durbin-Watson test is what we call the Lagrange multiplier test. Okay, Lagrange multiplier test, which is in our textbook on page 307. Okay, and then what is Lagrange multiplier test? Okay, we call the for short name is LM test. Okay, is by analyzing how well the lagged residuals explain the residual of the original equation in an equation that also includes all original explanatory variables. Wow, look at the explanation. Explanation is so complicated. But would you please refer to the page of 308 to our textbook for equation 9.16, okay, which is here, 9.16. Okay, look at the 9.16. This is this is also the 3 steps involved to do the LM test. Okay, first of all, obtain the residual from the estimated equation. So this is exactly the same as we did from Durbin-Watson's that no, excuse me, this Duren-Watson, we need to calculate the D based on the residual from the estimated regression. But for LM test, the first step is just obtain these residuals. Then what do we do from these residuals? We get to the second step, which is using the original residuals as an dependent variable. Okay, and look at the independent variable. Okay, is all the X variables and include also the lagged procedure. I think in this example, it shows that originally we have two X variables, two X independent variables. And since we need to compare with LM test with the Duren-Watson test, therefore we involve this just one leg of the residuals into this auxiliary regression. Okay, in that case, this is what we call analyzing. Okay, let's go back to the definition of this one. And by analyzing how well the lagged residuals, okay, means how well this lagged residuals, okay, explain the residual of the original equation in an equation that also include all original explanatory variables. So means that this is the original residual, this is the lagged residual. We want to analyze in how well this lagged residual explain the original residual, and in this equations also include the original independent variables, x1 and x2. So in other words, the purpose is to see how this lagged residuals related to the original residual. So in other words, we are checking let's see. Okay, so we're checking the null and alternative hypothesis about alpha 3. Okay, understand what I'm saying here? Alpha 3. Okay, so the third step is to use OLS to estimate auxiliary regression and test the null hypothesis that alpha 3 equal to 0. Then you're using the test, the statistic is using n times r squared. And n is the sample size, r squared is an adjusted coefficient of determination from auxiliary regression. And this test statistic follows for large samples. LM has chi-square distribution with the degrees of freedom equal to 1. Okay, so if LM is greater than critical value, then reject the null hypothesis. Okay, and remember, for Lagrange multiplier test is the two-way test. Okay, this is a difference from one-way test of Duren-Watson statistic. Although we know that most of the situation, this alpha 3 will be positive. But remember, the LM test for test alpha 3 is for two-sided test. Okay, all right. So I also like to show how to do the Lagrange multiplier test using eViews as well as the Gretel. Okay. So let me get to the my eViews. Okay, this is the, I'll put this down first. Okay, this is my e-views. If I want to do the LM test from e-views, okay, see it carefully. Click the function of view, okay, then choose residual diagnostic, then choose the second bottom called serial correlation LM test. You all see that? Then hit it, okay, and then they will ask you lags to include. Now remember that in these examples, we're going to compare the result from LM test to Durbin-Watson test. Therefore, we'll just include lag 1. So type it 1. Lag to include is just 1. And okay. All right. What do I have for this result? How come I don't? I'll make it bigger. Do I get this out? How come it's already here? Okay, look at this one. LM test. Did you see the result? LM test. And the statistic we're going to see, okay, I'll remember this one. The statistic we are going to see is N times R squared. N times R squared, right? Okay, so let's go back to see the result here. This is using observation times R squared, which is 8.4967. And it is the chi-square distribution with 1 degree of freedom. And the probability is 0.0036, the p-value. So isn't this is very small p-values compared with 5% or any others? You know, even alpha equal to 1%. So in other words, the LM test tells us to conclude, reject the null hypothesis. And since and end up with serial correlations. Okay, is that clear for the e-views working with the LM test?
Yes, clear.
All right. Let's see how do we do from the Grados. Okay, all right, Grados. After we have this output, okay, hit the test. Oh, okay, then choose autocorrelation. Okay, they will also ask you the lag order for test and hit 1. So, okay. All right. Where do we see? From the Grados, please see the middle one. Did you see this one? They are using, this is number 8.4967, exactly as what we have from e-views. And the probability P 0.0036, exactly the same thing as 0.00356. Y'all see that? Choose the middle one. There's other two methods, but the middle one is the same as what we say LM test. Okay?
Professor,
Yes.
may I ask a question? In the Gretel, we have to see the middle number, middle of alternative statistic. What about the meaning of the upper and the lower one? We just ignore them, or what the meaning of them?
This is, there's not only one way to test serial correlations. Okay, there's not only one way. And
Yes.
using these methods, there's 3 possibilities. This is all, I think in the articles, they all refer to all these values. They all revert to this test. Okay, and the one we mentioned in our textbook is called LM, Lagrange multiplier test.
Yes.
Which is the middle one.
I see. Thank you.
If you use the first one, this is another test, which follows F distribution. And there's another one, but it's also popular. The third one is called L-John-Box test. And this is also chi-square.
Okay, thank
if you
you.
study more about time series data, then you will later on, I think you may have the possibility to get to this kind of test and for other purpose.
I see. Okay, thank you. Thank you.
Rather, they just provide more than multiple Lagrange multiple test, LM test. Okay, but for e-views, if we want to do the LM test, and did you see this one, F test? Did you see this F test? This is exactly as what I have for the first one. Did you see that? The first one, I think from e-views, we do have this, they do provide this another test, which using F statistic. You all see that? Gloria, I think you will ask pretty good questions, e-views.
Yes.
Two ways. One is Lagrange multiplier test. The other one is what we call F test. Okay, and Gretel's provides three. The first one and the second one. And the first one is the same as the first one from e-views. Second one is the LM test, and the third one is another L-John-Box Q test. Okay?
Okay, thank you. Thank you.
So you all know how to do the Durbin-Watson and the LM test from both e-views and the Gretels. Okay, let me just stop here for a while and I'll let you have a few minutes to work on e-views and also Gretels to be familiar with the Durbin-Watson and LM test. Okay?
Okay, thank you. We will try it.
Okay, try it. Okay, all of you. Okay, and I'll ask you to show me how to do it next meeting.
Okay.
Okay, and I think I need to get out of my sharings. Okay, and I'll ask you to do by yourself. And if you have any questions, please ask, okay? Is Linda not here today? Okay, I think the first meeting is about the time. Let me just stop recording here. And